Hi everyone, my name is Adinda Karunia Maharani Damopoli. I'm from Civil Engineering Study Program, batch 2025. And today I'm gonna make my final assignment in my chemistry courses. So, my topic is chemistry applied in civil engineering with the main topic mineral carbonation technology. Why is this topic important? So, because the construction industry is one of the largest contributors to carbon dioxide emissions in the world. Cement production, especially, releases a huge amount of greenhouse gases because the manufacturing process requires very high temperatures and chemical reaction that produce carbon dioxide. Because of this issue, the researchers of the journal that I found are trying to find ways to make construction materials more environmentally friendly. One of the most promising technologies is mineral carbonation. This technology allows construction materials such as cement, concrete, and industrial waste to absorb and store carbon dioxide permanently. This topic is included in chemistry applied in civil engineering because it combines a chemical reaction with construction material technology to solve environmental problems. So, what is mineral carbonation? So, mineral carbonation is a chemical process where carbon dioxide reacts with materials containing calcium or magnesium. The reactions form stable carbonate minerals such as calcium carbonate. In simple terms, the process is carbon dioxide enters the material and the gas reacts chemically with compounds inside the material and a new mineral layer is formed and the carbon dioxide becomes trapped permanently. So this process is important because the carbon dioxide is no longer released into the atmosphere. In civil engineering, this process can happen naturally over time, but researchers now try to accelerate the process using special carbonation curing system. So how is it applied in concrete? One of the main applications is carbonation curing in concrete. Normally, concrete is cured using water. However, in carbonation curing, fresh concrete is placed inside a chamber filled with carbon dioxide gas. So inside the concrete, it will the carbon dioxide react with calcium silicate compounds, and the calcium carbonate is formed, and the concrete microstructure becomes denser, and the pores inside the concrete become smaller, and the result is early compressive strength increases, durability improves, water absorption decreases, and the concrete becomes more resistant to environmental damage. Sorry. The journal explained that concrete cured with carbon dioxide can achieve around 55 of its 28-day strength in only one day. So this means carbonation curing can speed up construction process while also reducing carbon emission. So, experimental results on concrete. The researchers have already conducted many experiments related to carbonation curing. The journal reports that carbonated concrete generally shows higher early strength compared to normal concrete. And some studies found that the 28-day compressive strength difference between carbonated concrete and normal concrete is less than 10%. In some cases, carbonated mortar even had slightly higher long-term strength. Researchers also observed that carbonation reduces porosity and creates a denser internal structure. However, there are still challenges. The first is specialized carbon dioxide curing chambers are expensive. And then the process requires concentrated carbon dioxide. And carbonated concrete may have lower pH, which can increase the risk of steel corrosion. Because of this, researchers continue improving the technology for safer and larger scale application. Magnesium-based cement technology. Besides ordinary Portland cement, the researchers are also developing magnesium-based cement. One important material is reactive magnesium oxide cement or RMC. This material is interesting because it requires lower production temperatures. It can absorb larger amount of carbon dioxide and it has lower net carbon emission. During carbonation, magnesium compounds react with carbon dioxide. New carbonate minerals such as hydromagnesite and nisconite are formed. The material becomes stronger and denser. The journal reports that RMC-based materials can absorb significantly more carbon dioxide than conventional cement system. Because of this, magnesium cement is considered one of the most promising sustainable construction materials. Use of industrial waste. Another important application is the use of industrial waste materials. Instead of throwing waste away, researchers use materials such as steel slag, fly ash, red mud, carbide slag, and blast furnace slag. These materials contain calcium and magnesium compounds that can react with carbon dioxide. For example, steel slag can absorb relatively high amounts of carbon dioxide, and fly ash and red mud also have carbonation potential. And carbonation can reduce the alkalinity of some waste materials. This application is important because it reduces industrial waste, it lowers environmental pollution, it supports sustainable construction, and it helps create a circular economy. Researchers also found that carbonation treatment can improve the physical properties of these waste materials. Recycled construction materials. The journal also discussed recycled construction waste. When old concrete structures are demolished, the waste can be crushed into recycled aggregate or recycled concrete powder. Researchers discovered that carbonation treatment can improve these recycled materials. The process works because carbon dioxide reacts with old cement paste. Calcium carbonate forms inside cracks and pores, and the recycled material becomes denser. Experimental data show that carbonated recycled aggregate concrete has better compressive strength. Chloride resistance improves, water absorption decreases, and the material becomes closer in quality to natural aggregate concrete. This technology is very useful because it allows old construction waste to be reused in new buildings. Challenge of mineral carbonation. Although mineral carbonation is promising, there are still several challenges. First is carbonation efficiency is sometimes low. Some materials absorb carbon dioxide slowly, making the process less practical. Second, industrial application is still expensive because carbon dioxide capture system cost a lot. Carbonation chambers require energy, and transportation and processing costs are high. Third, the researchers still need to study long-term durability, corrosion resistance, economic feasibility, and environmental impacts. The conclusion is mineral carbonation is a strong example of chemistry applied in civil engineering. This technology combines a chemical reaction with construction material engineering to reduce carbon dioxide emission and improve sustainability. The journal shows that concrete and cement can absorb carbon dioxide. Industrial waste can be reused as carbon storage materials, and recycled construction material can become stronger after carbonation. Magnesium-based cement systems have very high potential. Even though challenges still exist, mineral carbonation has a very promising future in sustainable construction and green engineering. This research proves that chemistry plays an important role in developing environmentally friendly civil engineering and technologies. Thank you. Thank you.